recording. Monday, again. Here we are. They keep coming. It's crazy. So last week we finished lines. Right? We talked about how do we find equations of lines, how do we find intersections of lines, right? We're going to keep working on the intersections of lines today in our new topic, which is this week we're doing optimization. That's an N there. So this week I'm going to introduce what's called optimization. It's a huge field of mathematics, as you can imagine, right? You want to optimize something, okay? And so optimization means you either want to maximize something or minimize something, right? Make your profit as big as possible or make your costs as low as possible, right? And so that's what we're going to work on this week. And then, just a reminder, I put it on here as well, but for next Monday, we're not meeting here. No, no, no. Okay? I'll post a video. As soon as I've made the video, I'll post it, so you'll have it. I'm hoping before the weekend, you'll have it. You can watch it anytime you want, okay? And I will introduce logic. So we'll be in a new topic called logic, which sounds easy, I think, but it's usually quite hard. So I'll introduce logic, but then, of course, when we see each other again next Wednesday, then we'll keep talking about logic. Okay? So I'll just introduce some terminology, some key things that we need to know, and then we'll keep working on it, of course. Okay? So logic is not in the textbook, so I'm just going to post. I can't remember if I've posted. It looks like I haven't posted it yet, but I'll just post a handout. Okay? Does anyone want a printed out handout? 1, 2, 3. Still at 3. Okay. Take, and then +1, 3. I'll try to remember. Maybe I have some spares in there. Remind me after class. But because it's not in the textbook, I can print it. But wait, hello? Let me just mute everyone here. How do I mute all? Sure. Okay. So then, I guess I didn't show it. The following week, we're getting ahead of ourselves, right? We meet on Monday, we'll do review for the test. Okay? I'll give you a practice test, and we'll do review, and then we have test 1 on October 8th. Question? Not yet. So, but I have highlighted the formulas that will be on the formula sheet, but I need to do that. Just as soon as I leave this room, I forget. Do you mind sending me an email to remind me? I know. Put it on you. Is that okay? There. That's all I need. I just need something in my inbox because my inbox is my to-do list. So if you just send me something, then I'll do it. But if I walk out of here, no, I won't. Okay. So, oh, what happened? It went away. I don't know where it's going. It's just jumping to, okay, it doesn't want to be there. Whatever. That's okay. That's okay, I guess. So we're skipping chapter 2, right? We're not going to do it. You're welcome to read it if you want to, but only if you're interested in matrices. So chapter 3 is called linear programming. And let me just, I need a little bit more space here. Linear programming, well, we know one of these words, linear, right? That means that we have lines. So lines, which means we'll be working with something like y equals mx plus b or some version of that, right? Ax plus by equals c sometimes, right? Make it a little bit trickier, but you can still work with it. So that's why we had to spend so much time learning about lines, because now we're doing linear programming. And the geometric, we're not doing any other approach, so don't worry about that. But the programming part is the optimization aspect. And so in this chapter, it looks simple enough. We're going to solve linear programming problems that maximize the objective function. We'll learn what the objective function is. That's a good place to start. And then we'll solve linear programming problems that minimize the objective function. And like I said, together, these are optimization. Like I said, optimization is a huge field in mathematics. And what's really fun is that UBCO has kind of the biggest optimization program that I've heard of. So that's kind of neat. So that's what they're doing up there, optimization. They're doing other stuff too, but in terms of math, that's their heavy hitter. So it's in this blurb, but I will kind of read this, and then we'll talk about all the new terminology that we've introduced. Okay? So we're going to focus on maximization problems. Okay? We're going to spend a lot of time learning how maximization problems work. Okay? And then we'll introduce minimization problems, but they're less common. So that's why we focus on maximization. And but then we'll do a couple of minimization. We do the same thing. So what is that same thing? So a typical linear programming problem consists of finding an extreme value of a linear function subject to certain constraints. Yikes. What does that mean? Not entirely sure yet. How about this? These constraints are things like if you are producing a product, you only have so much material. You only have so many hours of labor that you can use, right? Maybe you only have so many machines, right? And so what we can do is we can construct lines that involve maybe the number of machines that I have and how many hours of labor I have. And then I have lines for that. And then I'll be able to optimize those. And so we're either trying to maximize or minimize. And so those are the constraints. Right? I'll make a tiny note here. Time, labor, material, etc. Just as an example, I'll write it nicely later. So we're either trying to maximize or minimize the value of this linear function, where we want to maximize profit usually, or revenue, right? That's a good thing to maximize. You want as much money as you can, right? Or we want to minimize the cost, right? And then so you want it as low as possible. Okay? And so, and I'll skip this part because we already talked about it, but the function that we're trying to optimize is called an objective function. And so, and the conditions that must be satisfied are called the constraints, which we already know are things like, I'll write this nicer, time, not nicer, labor, material, things like that. Okay. So what does this look like for us for a problem? Okay. So optimization problems, optimization problems. Often they're given as word problems. Now those can be really tricky, right? And so what I will do on the test and on the final exam is I will, and it will be on the test and on the final exam, of course, so it's good to be ready, is I will give you the first two parts, okay? Which are the hardest two, I think, or at least then you can be sure that you're using the right thing at least. Okay? Now, what are these things? First thing you want to do is you're going to identify the function you want to maximize or minimize. I'll just do max or min. Oh. This is the objective function. In our examples and in the assignment, well, we'll see. Maybe I'll give it to you in the assignment so that you have a better idea of how to do it. But in the examples, we'll have to find them, right? On the test, they will be given. So I do want to make on a test, the objective function will be given. And I know that doesn't mean anything yet. It will. So from the word problem, you have to identify which function you want to minimize or maximize. I guess, oh, I forgot a piece. Or I just add it here. Can I do that? Can I cheat? This involves identifying your X and Y. What will be your X and what will be your Y? This involves identifying X and Y. Right? What do they represent? I'll put that in brackets. What do they represent? Then we'll have a list of constraints. Things like, well, you only have 15 machines you can use, right? And maybe you only have 30 hours of labor that you can use, right? So how do you distribute those? Uh, and so then you're going to identify the constraints. These are really kind of limiting factors on X and Y. And on a test, the constraints will also be given to you, which is nice. On a test, the constraints will be given. Now, these constraints are going to be lines, right? And so the constraints are, these are lines. And usually what happens is these constraints, right? We have the constraints like, I only have 15 machines, so I can't pretend that I want to use 16 machines, right? And so I can use up to and including 15, but no more, right? And so then I have limits on these things, right? On my constraints, which means that we're going to have to work with inequalities, right? Less than or equal to this line. And so the constraints will involve inequalities such as maybe something like 2x plus 4y has to be less than or equal to 30. Something like that. Whatever x is, whatever y is, right? Machines and labor maybe. Or product 1, product 2 that I'm able to produce, something like that. And so now these inequalities, how are we going to draw these inequalities? So we know how to draw a straight line, right? We know how to draw, oh, and I guess I haven't said it yet, but we're going to have to draw these lines. We have to draw them on a graph. I think I said it briefly. Maybe I'll hold off on the inequality because it's going to be kind of a long explanation. And so I'll finish the list of things that we need to do and then come back to it. So, because then we'll have the overview. So we'll have the objective function, right? Thing we want to maximize. We'll have constraints, and those will be given to us. Right? I'll tell you what they are. What you want to do is graph the constraints on the same graph. So we graph all the constraints on the same graph. Yeah? And I'll write it down later, like I said, but to graph this constraint, something like 2x plus 4y is less than or equal to 30, you can just graph 2x plus 4y is equal to 30, and then the less than or equal to means you're going to shade a region. Right? So it applies to a certain region, either below or above. And I'll give you a way that you can check which region it is if you're feeling unsure. So we're going to graph the constraints on the same graph. Then we're going to find the feasible set. Okay? Now the feasible set is the region, and sometimes it's called the feasible region. I'll call it the feasible set probably. But it's the region where all the constraints are satisfied. So what you want to do is you want to find the feasible set or feasible region. Which is where all the constraints are satisfied. Which is where all the constraints are satisfied. So just as a quick sketch to show you what this could look like, maybe you have a constraint that looks like this. Maybe you have a constraint that looks like this. Pretty common. Just kind of two different constraints. You've graphed them. And usually we have constraints that x has to be greater than 0, which means we're on this side of the x-axis, and y has to be greater than 0, right? Because I usually can't sell negative things, right? And so, but those will be given in the problem. Now this region here, let's say, if everything has to be below each of these lines from our constraints. Now these are made up constraints. We'll see real constraints, obviously, but usually for a maximization problem, the constraints look something like this. And so it has to be less than or equal to something and less than or equal to another something. Now this is what we call the feasible set. Feasible. Oops. I better just start over. Oh. The feasible set is the region where all the constraints are satisfied. Now, what's cool about linear programming is, just as a fact, the function, the objective function that you want to maximize will be maximized at one of these intersections. So that means that our next step is to find the intersections of the feasible set. So, fun fact, the objective function that's way back from step 1, right? We haven't done anything with it. We've been graphing the constraints so far, right? And so we kind of make the objective function, then we forget about it until the very end. Okay? But the objective function is the goal of this problem solving. Let me just add a page here and grab my fun fact here. Whee! The objective function will be optimized. Oops. At one of the intersections or the intersections we're going to start to call vertices, a vertex, or vertices. Going back to our example, all of these orange dots is a vertex. Vertex 1, 2, 3, 4. So the objective function will be optimized at one of the intersections, or we'll start to call them vertices, which means we need to find the intersections. Find the intersections, which means we need to find the intersections of the feasible set. So that's your next step, is to find, well, where do all these intersections happen? Once you have the coordinates, the XY coordinates of your vertices, once you have all the XY coordinates of the vertices of the feasible set, I tend to set it up in a table. I think that's the cleanest way to do it. We construct a table. Oops. Construct a table like this. So it'll have the vertex, right? XY, XY. Of course, each of those XYs will be different because you'll have all your vertices. And then you'll have your objective function. Maybe it's something like the profit is 100 times X plus 200 times Y. Seems like a reasonable profit function, right? If I sell item X, I get $100, and if I sell item Y, I get $200 per. And then I plug in X and Y, and I can calculate how much profit I make. So then, at each vertex, so at each x and y, what you're going to do is you're going to plug in that x and that y and find the profit at each vertex. So then the profit at the first vertex, and then I'm going to cheat and just copy paste and do the second vertex, etc. We know that from this list of potential profits that we could make, then I'm trying to probably maximize the profit. Right? So from here, from the list of possible profits, right, we go back to our fun fact. The objective function will be optimized, right? So it'll be maximized or minimized, depending on what we want to do, at one of the intersections of the feasible set, which I didn't say till later. And so one of these will be the maximized profit. So then 7 from the table of possible profits, or I should be generic in this one, I guess. And then I'll do as an example of the profit. From the table of possible objective functions, select the optimized answer. For example, in the table above, we want to maximize profit. So you select the vertex that yields the highest profit in that list. So you select the vertex that yields the highest, right, or max, I should say, profit from the list. And then you're done. Then you've maximized your profit function, for example. Right? There's a lot of work to get there. What's nice about this work for me is it's a way to practice or seeing whether you know how to graph lines, right? Do a little bit of inequalities, not too much, but a little bit. And then finding the intersections, right? That's some work that we've already done, right? So we already have all these skills, but now we're putting them together. Question?
Sorry, so the vertices are the intersections of...
Yes, but only of the feasible set. Before we do an example, because I think it'll be more clear once we do an example to see how it all works. I want to just talk about how do we graph inequalities. Graphing inequalities. Oh, and then I should say, once you've picked your highest profit, of course, you're done. Now I'm on to something else that we'll need. So if you want to graph, for example, to graph something like 2x plus 4y. Or how about I make it nice and easy for myself? How about 4x plus 2y is less than or equal to 10? That's nice. This is a typical setup of a constraint. And usually it is less than or equal to, right? So if you're comfortable with the less than or equal to, this here is less than or equal to. I feel like we already talked about the L, right? How it makes an L, or did I not talk to you guys? I'm doing inequalities in all my classes. Okay, so then see how this symbol makes an L. If you make your L like this to know that this is your left hand, right? It makes an L. And so then if you read it, just how, if it makes an L, then you can read it as less than. And then with the line underneath, it's less than or equal to. And then if it's the other way, it's greater than. But you really only need to remember one, and then if it's not that, you know what the other one is. Right? And so let's just do we've got less than or equal to, a less than with no line underneath, right? That's just less than but not equal to. The other way is greater than or equal to. And of course, the other way without a line is just greater than. And I guess I should mention not equal to, which I think is probably more familiar. Not equal to. For the most part, we're going to be working with this symbol, so that's why I want to do an example with it. So if we have something like 4x plus 2y is less than or equal to 10, what we're going to do is just treat the inequality as if it's an equal sign. Because we want to draw the line, and on the line, it is equal to, right? And so this portion, the equal to part, is the line. Right? And then the less than shades the region that satisfies that. So to graph it, to graph, I'll do 4, I'll just put it on this fresh page. Oh, you know what? I don't want to move stuff around, so I'll just add a page here. To graph 4x plus 2y is less than or equal to 10. Pretend for a moment that the inequality is an equal sign. Pretend the inequality is an equal sign. All right? Which puts us at 4x plus 2y is equal to 10. You know how to draw that. Right? This looks wonky. There. Oh. So now on your grid, and I'll give you an empty grid. So that means that you'll have to figure out what your ticks are and things like that. But that's all part of the drawing the line work, right? And so on the grid, which on a test will be given, right? On an assignment, it's not given. So on the grid, draw 4x plus 2y is equal to 10. How do we do that? Pick a value of x, plug it in, figure out what the y is, right? Do that twice, or pick a value of y and figure out what the x is, right? Let's see here. Let's do blue. Find 2 points on the line. I usually just like to plug in values of x and solve for y. 4x plus 2y is equal to 10. If I let x be 0, that makes for easy math. All right. 4 times 0 is 0. 2y is equal to 10. Means that y must be 5. So when x is 0, y must be 5. I'm picking 1, even though the math's not beautiful, but we can still handle it. I get 4 times 1 plus 2 times y is equal to 10, which means 4 plus 2y is equal to 10, so 2y is equal to 6. I actually did the math wrong in my head. It works out. Woo! Y is 3. That's great. Okay. So now, once you have your 2 points, and you can do more if you want, but we're just doing this one little line. Maybe I'll have 1, 0 here, obviously. 2. 3, 4. Once we have our points, we can graph them. When x is 0, y is 5. That's why I needed that guy there. So high. When x is 1, y is 3. So something like this. Then, like all our lines, we take a straight edge. I'll use the edge of my calculator maybe. It's not terribly important because we're going to solve mathematically where the intersections are, right? You're not going to look at the graph to find the intersections, although it's nice to have an idea. Right? You have to show me that you know how to solve for it anyways. So that's why it's not super important that the line is perfect. But something like this. Yeah. You'll get a little grid section. Yeah. Okay. So here's our line, but this, remember, is the line for 4x plus 2y is equal to 10. Okay. But we wanted to graph 4x plus 2y is less than or equal to 10. Okay. Which is a region. Okay. And so what you want to do, I can tell you what it is. Okay. It's going to be this region, everything below it. That takes practice, right? It has to be below the line. Okay. How can we know for sure? Well, you can pick a point that you know is somewhere below the line. So you see how the line keeps going forever and ever, and you're either below it or above it, right? And so you pick a side, right? I'm gonna pick a side in here because I know the coordinates. Maybe I'll pick 1, 1. We can pick a test point to check the inequality. If the inequality is true, right, then that point is in the region. If it's not true, it's not in the region. And so we can pick a test point to see if that point satisfies the inequality. If it does, the test point satisfies the constraint. If it does, or I should say, no, that is what I should say. If it does, the test point satisfies the constraint. So if I put in into 4x plus 2y, and I want to know, is it less than or equal to 10? Right? I'm going to plug in x is 1 and y is 1. Right? And it doesn't matter which point you pick in here. Just pick one that you know is in a region. Okay? So now you have 4 times 1 plus 2 times 1. Is it less than or equal to 10? Well, 4 plus 2 is 6, and 6 is less than or equal to 10. Whee! And that's what tells me that, okay, then my arrows, which I like to do because it gets kind of messy if you're shading. We'll shade as well, but for now we'll just do arrows. So this confirms that this point is in the or satisfies the constraint, which means the arrows have to cover that point. And so here, this confirms the arrows for the constraint must include the point 1, 1. By a similar method, right? What could you do? What if you picked a different test point? Right? What if you picked, I don't know, 3, 3? I know that's on this side of the line now. If I use x is 3 and y is 3, then I get 4 times 3 plus 2 times 3, which is not less than or equal to 10. Right? And so you just pick a point that you want to try, and if it works for that point, it'll work for all the points on that side of the line. That takes some practice, right? That's not something that you've probably done before, right? But oh, got double questions. We'll go 1, 2.
Yeah, so basically you can choose a kind of test point as long as it's like inside the point and feasible set.
Yeah, so we're trying to find the feasible set, but because the feasible set will be the overlap of all these regions, which means that we have to find the region first. But what this means is that this, because 1, 1 did satisfy the criteria, it means that everything below that line satisfies the constraint, which means you ignore the rest. This side of the line, it doesn't work, right? Maybe I don't have that many machines or whatever.
Could you technically put like a point on the line you have already drawn? So like 1, 2, or 2, 1, I guess.
If you're trying to find which side the arrows should point to, then being on the line doesn't tell you anything, right? Being on the line is on the line, but we've already drawn the line. So then you want to see, okay, which region satisfies it. Nice. Like I said, little bit of it. We have all these skills, but now we're building on just a little tiny bit more, and a little bit more, and a little bit more. Okay, and a little bit more. But after that, you know what to do. No, not yet. Okay. So what you're going to do is you're going to do this on the same graph with all your constraints. There's usually about 4 or 5 constraints that you have to deal with at least. Okay? And so that means that you'll have multiple lines and multiple areas, right? And where they all overlap, that'll be your feasible set. Okay? What's nice is if you're using Desmos, you can give it something like 4x plus 2y is less than or equal to 10, and it'll show you the shaded region. Ta-da! Wait. I don't know why it's doing that. It's, I don't know, maybe I'll restart it. Where is it? There. Okay. So you can always check with Desmos, but you won't have Desmos on the test, right? Okay. And so that is how you graph inequalities. Nice. To find, or I'll do it in green, to find the feasible set, we map all the or graph all the constraints on the same graph. We graph all the constraints on the same graph. And where they all overlap, that's your feasible set. And the region where they all overlap, and the region where they all overlap will be your feasible set. Woo. Okay. Any questions before we do an example? First example. Yeah. Yes. As long as you kind of keep track of, okay, on this side, it does work, right? And so then I shade it. And then if you pick a different point out here, then it wouldn't work. Then you shade the other side because that's the side you want. But you can. Uh-huh. Okay, so what do these things look like? Oh, maybe I'll add a page here. Word problems, we heard that. Any sort of person who doesn't like math always kind of, as soon as you say word problem, oh no. They are hard. They are. But luckily, I'll give you the things you need out of the word problem. Yeah. You got it. Is that good? Fair enough. I'll keep talking about how hard word problems are. No. Once we have the things that I'll give you, they're not so hard. But it is really hard to construct the objective function and the constraints, right? But remember, I'll give those to you on the test. You still have to practice on your assignments and do them, but on the test. Sorry, I feel like I got the look. Good? Yeah. Here's our first example. Nikki holds 2 part-time jobs, job 1 and job 2. She never wants to work more than a total of 12 hours a week. Okay, fair enough, I guess. She is determined that for every hour she works at job 1, she needs 2 hours of preparation time. And for every hour she works at job 2, she needs 1 hour of preparation time. And she cannot spend more than 16 hours for preparation. Not entirely sure what kind of job she does, but here we go. Maybe she's a teacher. I don't know. If Nikki makes $40 an hour at job 1 and $30 an hour at job 2, how many hours should she work per week at each job to maximize, oops, let's do it in yellow, maximize her income? We want to maximize the objective function. Yeah? And so we want to maximize the income, which makes this the objective function. But what is the objective function then? The income we're told, just working backwards here, right? But the first step that I would say is figure out what you want to maximize or minimize, and that will be your objective function, and then work backwards from there. So if the income is $40 an hour at job 1 plus $30 an hour at job 2, right? However many hours at each job. And how many hours should she work per week at each job? Which tells me, because with practice, right, you need an X and a Y. And so what if we just write out her income, which is 40 times hours at job 1 plus 30 times hours at job 2. the values in my objective function, right? Which this is my objective function. Just squeeze it in there. Is my income function. That'll help me figure out what my X and Y have to be. I always let them be in the order that they appear. So from here, I'm going to let X be the number of hours at job 1. And I'm going to let Y be the number of hours at job 2. If we do shorthand I for income, this becomes 40x plus 30y. Looks sort of like a line. Huh? 4x plus 30y equals some amount of income. Huh? This is tricky, right? Figuring out what your X and your Y are. Right? And so I'm going to get you on the test, I'm going to get you to tell me what the X is and what the Y is, right? Because I'll just use X and Y, I'll just give you this, right? And then from there, you need to figure out, okay, well, what must my X be and what must my Y be from this word problem? But that's as far as I'm going to get you to go in terms of interpreting the word problem too closely. So I'll give you this, but you will need to tell me what X and Y represent, just like here. Okay, we've got our objective function. That was our step 1. I'll do that here, sorry. Step 1. No point in having steps if I don't follow them. Step 2, using that X and Y that I just established, right, we need to write out all our constraints. So, to find the constraints. Sometimes these are hard to find, but they'll be given in the problem. So the first constraint is that she never wants to work more than a total of 12 hours per week. Right? It seems to me like she would work less if she could, but no more than 12. How do we get to the number of hours per week that she works? Well, that's going to be the number of hours at job 1 plus the number of hours at job 2. And so the constraints can be, first we have the hours worked constraint, which looks like this. X plus Y must be less than or equal to 12. That deals with this first or second sentence, I should say. All right, she never wants to work more than a total of 12 hours a week. You got it. She's determined that for every hour she works at job 1, she needs 2 hours of preparation time. And for every hour she works at job 2, she needs 1 hour of preparation time. And the constraint is she cannot spend more than 16 hours for preparation Right, so this is another constraint that we're adding. And so I'm gonna call this the preparation constraint. If you had to figure out, well, it takes her 2 hours per X, right? So times X for job 1, right? 2 hours of prep for the question? No. 2 hours of prep for each hour at job 1. How many hours? She needs 1 hour of preparation time for job 2. I'll do 1y for now, but you can just write y if you want. But I just want to highlight that it's 1 times y, just in case. And our constraint is that she can't spend more than 16 hours. She can do less, but not more. Yeah. Good. Look at us picking away at this word problem. All right. So we dealt with this one, and then we dealt with all of this. And we already dealt with the last line, so that's good. Yeah. There are some hidden constraints. Can you work negative hours? No. Right? And so usually it comes standard, but we always have to say that X has to be greater than or equal to 0. Right? I have to work at least 0 hours at job 1. And same thing, I have to work a positive number of hours. It can be 0, right? But it can't be negative at job 2. Right? What do these little guys do? These just make sure that on your graph, you're just in that positive quadrant, right? So it makes the graph look really nice. Right? So what these force is that you're only working in this region. Right? So that's nice. Because X has to be greater than or equal to 0. Oops. This way and this way. And Y has to be greater than. So these constraints will be listed, right? But they're just simplifying your graph a little bit. Okay. Nice. Luckily, I'll give you these. Right? That's nice. That's so nice. All right. We found the constraints. Now what? Now we have to graph these constraints. Let me make sure in my list, was that my next thing? Identify the constraints, graph the constraints. Phew. Almost like I've done this before. 3, graph the constraints. I want to highlight, I probably shouldn't. It's going to be one of those things. What do we do with this? So this first part, we don't use it until the very, very, very end in the table. All right. So we started there and then we parking lot it, we forget about it, and it doesn't come into play at all until the end. And this guy here. But we do have to graph our constraints, these guys. Okay. I know how to graph x plus y is equal to 12, right? And with practice, we'll know that below means this region, right? But that's hard to know, right? You don't have to show that you've used a test point. I just wanted to show you that you can use that, right? And so let's see. Oh, sometimes there's stickers. Little grids. Where though? I don't know. Here? Oh yeah. Cheating, I know. I have to find 2 points on x plus y is equal to 12. And then I have to find 2 points on 2x plus 1y is less or is equal to 16 to draw the lines. Just so I can get an idea of how wide my x-axis has to be and how tall my y-axis has to be. Because my y-axis and x-axis are always going to be part of the feasible set, right? From here, these will always be constraints. Then I recommend trying at x equals 0 and y equals 0, right, as your points. Might be useful. So for if x is 0, then x plus y is equal to 12. Looks like 0 plus y is equal to 12, so y must be 12. And if y is 0, I can see that x must be 12. Because the math is kind of breezy. That's nice because now you know the whole stretch of your xy axes, right, for this line. We still have to accommodate the next line. 2x plus y equals 16. So 2x plus y equals 16. Let's put x equals 0. Then I get 2 times 0 plus y is 16. Then y must be 16. How about at y equals 0? Just because the table got a little messy in this case. Then I have 2x plus 0 is equal to 16. Oops. So x must be 8. For each of these lines, I guess I should use a different color. How about, they should be dark enough to see. Was different enough. Otherwise, I might get confused with my points. Right? Okay. So it looks like if my x is 0, y goes to 12, and if x is 12, y goes to 0. Okay, so I've got kind of a 0 to 12 range so far. But then when I look ahead, x is 0, y is 16, which means I need to go up a little bit higher to get to 16. X is equal to 8 when y is 0. That's inside 12. So it looks like for sure I need to have room for x equals 12, y equals 16. All right. Takes a little bit of practice to do that, but let's see if we can do it on this graph here. How many points do I have? 1, 2, 3. Okay. I'll do my graph down here. My X, my Y. And let's see if we did it. 1, 2, 3, 4, 5. Guess this one wasn't the concern. 11, 12. This one is, but I can tell I'll have room. 1, 2, 3, 4, 5, 6, 7, 8, 10, 12, 13, 14, 15, 16, just. Go to 17 just for good measure. Okay. My first constraint is going to be the light blue line. When x is 0, y is 12. When x is 0, y is 12 here. And when x is 12, y is 0. I'm going to go ahead and connect those right away. Because like I said, otherwise it can get confusing. Right? Which points go with which line. For my second constraint, the dark green line, I have when x is 0, y is 16. And when y is 0, x is 8. Take my straight edge, which I'm using my calculator edge, I guess. It's like this. Ah. Now we have to find the feasible set. So graph the constraints. And the feasible set means that we have to find where the less than or equal to 12 is satisfied. Right? And the less than is always going to be below the line, but I also know that that's hard to see sometimes, right? Until you're used to seeing it, it'll be on the other side, right? So I'll just show you where it is. It's going to be everything on this side and everything on this side of the green line. And for the blue line, you had to pick a point as a test point. I would say it might be nice to pick a point that is on the same side of both the lines, right? And so I would pick something kind of easy like 1, 1. I always pick 1, 1 if I can, because it's easy, right? So then we can check, okay, 1 plus 1 is 2, which is less than or equal to 12. Good. How about 2 times 1 plus 1 is less than or equal to 16? Good. Right. 1 is greater than 0. Whoa, okay. We're using it here too. 1 is greater than 0. Still true, right? And so what we'll add are these constraints, but like I said, it just makes your graph look nicer when we have only those areas pointing in, right? This is saying that y is greater than or equal to 0. And this is saying that x is greater than or equal to 0. They have to be positive. Now, there are different ideas. Okay? I like these lines or these arrows because they don't get so messy. Right? If you were shading and shading, it can get hard to see the overlap. And another method that you could use that I don't really use is you shade the side that you don't want, because then your feasible set is everything that you do want and it's clear. But that's harder to think about, right? I think we shade the area we want is more natural, but right. So you can do it whichever way you want, but which region is in our feasible set here? Let's see here. 4. Find the feasible set. Well, I know working from 0, 0, right? I know I can move out until I hit a line. Right? And so that's usually how I like to draw the feasible set is I like to start here at the origin and just draw until you hit a line. And then keep going. I know, it's like coloring. And you only can go as far until you've hit a line, and then you have to stop. Because otherwise there's no more overlap. This is our feasible set. Okay. Nice. That's a lot of work. And I'm curious to know what time it is. Oh my gosh. Good thing we're close. 1 example per day. I was just telling Joya, who I share an office with, I was like, oh, I'm kind of worried. Last term, it took me a whole class to do 1 example. Well, it's the same. Will be the same. Exactly the same. That's okay. It's our first one. Okay. Now what? Our fun fact. Our objective function, which is what's her face? Nikki. Nikki's income. Forgot who we were helping here. Nikki's income, that's what we're trying to maximize. Right? And so, well, the fun fact is that the income will be maximized at one of these intersections, including 0, 0. But that's never an optimal solution. It is a solution, but it's never optimal. So we want to find the vertices of the feasible set. Most of these will be relatively simple. Right? And then there's usually one that requires a tiny bit of work to find the intersection, 1 or 2. Okay? So, well, I guess let's use orange because I haven't used see labels on the graph. Oops, I made that one word. See labels on the graph. I always like to start down at 0, 0. And I call it A. Otherwise, I usually forget about 0, 0, but you want to include it as one of your options. Okay? And so that's why I start there, and then I work my way around clockwise, and I'm just labeling these vertices. And so if that's A, then this can be B, and this is a vertex. That's where two different lines cross. Call that C. Call this D. Different color might have been nice, I guess, but it's kind of too late now, I think. Can you see it? Yeah, okay. But if the back can see it, you're okay. Yeah.
So do you want me to do a one per equation that you did, like one for the green line, one for the blue line, and then the 0, and then again?
So what you're looking for is just the vertices of the feasible set. So because this guy is not in the feasible set, you can ignore him. Yeah. But because where one of them, or where they cross on at one point on the y-axis and one point on the x-axis is usually in your feasible set, it's nice to have those already. All right, save you a little bit of work. Okay. See the labels on the graph. Start at 0, 0, labeled A, then move clockwise. Gonna need more room. But I also need this here. Whee! Okay. A, we know is at 0, 0. So you don't have to do any work there. B, because you've already shown me that 0, 12 is on the line, right? You're allowed to use it. If you didn't have this work shown here, you would have to show me that when x equals 0 on x plus y equals 12, then y must be 12. Right? But that's pretty simple. How about, just for good measure, let's write out the work as if we hadn't done it. But like I said, if you've done it, you don't have to show the work. B is the intersection of x equals 0, right? The y-axis is at x equals 0. Right? That's from 1.1. You know that, right? And the green line, right? The blue line. Nice try, Emily. Which is x plus y is equal to 12. Usually I like to x plus y equals 12. Put them on here so I don't do what I just did. 2x plus y equals 16. There. Now it's easier to see, I think. So, and x plus y is equal to 12. Well, at x equals 0, I'm technically using the substitution method, right, to find the intersection. X equals 0, y is 12. So then B must be at 0, 12. Not a ton of work. C. So point C is at the intersection of these kind of interesting lines. 2x plus y is equal to 16 and x plus y is equal to 12. This is the one that's going to require a little bit of work. It's at the intersection of 2x plus y is equal to 16 and x plus y is equal to 12. However you want to solve this, right? Either by substitution or elimination, if that's what you're more comfortable with, right? It doesn't matter, but you have to find the xy coordinates. I'll use substitution, and I'm going to solve for y in x plus y equals 12. I'll make a note here. Solve by substitution or elimination. It doesn't matter. Might be nice if you write me a note saying which one you'll do, then I can follow it more easily, right? But if I have x plus y is equal to 12, then y is 12 minus x into 2x plus y is equal to 16. Then I get 2x plus y, which is replaced by 12 minus x, which is 16. And I get 2x minus x is x plus 12 is equal to 16. Woo! So x must be 4. Yeah. Good. What's nice about having a graph is you can usually check to confirm that that makes sense, right, before you go ahead. And so if I'm at x equals 4, does that look reasonable? Phew, it does. So I can trace it up, and that looks like x equals 4. And so I'm on the right path. But you do have to show your work, right? Which means that y is 12 minus x, which is y is 12 minus 4. So y must be 8. Which means that C is at 4, 8. Another reason you don't want to use the graph exclusively, right? It's just to check your work, is because sometimes the answer is 4.2 and 7.9, right? It's not always exactly right there, right? But it's nice to have an idea of where it is. So is it at 4, 8? Looks good to me. Yep. And then finally D, point D. D, oops, I had it lined up over. D is the intersection of what? So you want to make sure that you're using the right line. D is the intersection at y equals 0 and 2x plus y is equal to 16. Which means that 2x plus 0 is equal to 16. So x must be 8, which we already did. So the point is at 8, 0.
Instead of like solving for it, could you not just be like, I mean, I can see on the graph that like the point is always the 8.
Yeah, so the answer is it depends. If you use y equals 0 as one of your points, which is why I would recommend doing that, right? Use x equals 0, then y equals 0 as your 2 points, then you don't have to show the work because you've already done it, right? Or you could even say the point D is at 8, 0 as shown above, right? If you've shown it above. If you haven't shown it above, you have to show it now, right? Yeah.
With the point of like D,
Mm-hmm.
could you, when you say the intersection of y equals 0, are you doing the opposite of what your point is actually on? Like the point is on the x line right now?
Yeah, so, but the equation for the x-axis is y equals 0. So it's a line at y equals 0. And the equation for the y-axis is x equals 0, which is nice to look at. Nice. Okay, that was 5. Step 6, even though yeah, okay. I feel like I had 7, oh, because the 7th step, let me just confirm. Okay, is just picking the right answer. Construct a table of the vertices. I'll say see next page because I need more room. Remember, there's only 7 steps, so we're getting close. A lot of work. But you always follow these same steps. That's nice. Okay. The reason I like to have the labels is, oops, ABCC, ABCD, so that I can label them in the table as well. And then I'm not jumping around. A was at 0, 0. B was at 0, 12. C was at 4, 8, I want to say, but let me just confirm. Yep. Thank you. And D was at 8, 0. Now, the objective function was I, the income. If you want to call it profit, that's okay. But the income, notice that we haven't touched this thing since the very, very beginning, but now we grab it. 40x plus 30y. That's the thing that we want to try to maximize. So 40x, oops, 40x plus 30y. So the income at vertex A is a boring $0. You work 0 hours and 0 hours, you get $0. Fair enough. What if now it's more interesting? 40 times 0 plus 30 times 12. Let's see here. 40 times 0 is 0, but what's 30 times 12? That sounds pretty good. I get $360. Okay. That's better than 0. Huh? What's the next one? When x is 4 and y is 8, I get 40 plus 4 Nope. 40 times 4. I'll just jot it down here since I bungled it. 30, I almost did it again, times 8, 240. Ooh, $400, unless I did it wrong. Good. Can I get a confirmation? Yeah, good. Thank you. 40 times 8 plus 30 times 0. 40 times 8. Now, compared to the rest of those options, I don't want $320. I want 400, right? And so now, oops, I like yellow here. Step 7, pick the vertex that maximizes the income. Nikki should work 4 hours at job 1 and 8 hours at job 2 to maximize her income to $400. Nikki should work 4 hours, right? Because our X is the number of hours at job 1. At job 1. And 8 hours at job 2 to max her income to $400. You did it. What I want you to do, we will go through these examples on Wednesday, right? But I want you to try setting up the objective function and the constraints. It's really only this one, because this one is just basic for some reason, but it's a third example. It's kind of confusing. But I want you to try setting them up for this one and try solving it. And we'll pick up there on Wednesday. Question? Oh, yeah. Wait, what did I do? With that, I release you. See you on Wednesday. I'm just going to stop this here.